The next technology guide we're going to look at is cold ions, obtaining robust configurable multi-qubit gates. Most of the tools QControl provides work across all platforms, but sometimes a particular quantum computing hardware platform may present a unique control challenge. In this case, a custom tool needs to be built. A great example of this is with cold ions. If you want to create an entangling operation between each of the qubits, you have to exploit a special trick where you use a laser to essentially kick the ions and couple their internal state to their mechanical modes. If you do this just right and decouple these mechanical modes afterwards, you can create an entanglement between two of ion pairs or more. If you tried to simulate this type of gate, you would find that it would become rapidly intractable, as the Hilbert space grows exponentially with the number of modes and the number of ions. Fortunately, we can exploit a special trick and assume the Hamiltonian takes a specific form that is both physical and analytically tractable. QControl provides a module which exploits this trick and provides Mormon-Sorensen-style gates for creating entanglement between ion pairs. Using this package is as easy as providing us with some physical information about our system. For our first example, we're just going to consider two ions in a trap and create entanglement between them. So you tell the package the number of ions, the particular type of atoms they are, and important information like the frequencies of the trap. Then you tell us the particular target operation you want to achieve. In this first case, we're going to create an array which tells us that we want to create entanglement between the 0 and first ion with a phase of pi on 4. This information is then fed into our optimizer, and calling it is as simple as optimize. In this first example, we're going to create an optimal pulse. These pulses will just create the correct operation and will not necessarily be robust. Once the optimization is complete, the controls are returned to you. These are in the form of amplitude and phase modulations, which should be applied to the lasers which kick your ions. If you want to create a robust pulse, which is robust to, let's say, the relative detuning between the lasers of your ions, then what you do is you simply add an additional flag to the configuration. You say robust equals true. This adds additional constraints to the optimization problem, and new pulses are created, which are robust to these kinds of errors. If you then want to verify that these pulses have done the correct thing, we provide a few special tools. The first thing we provide is phase space diagrams of the mechanical modes. You can see that in this, for the optimized case, both of the mechanical modes happen to close after the operation, ensuring that the internal modes and mechanical modes are decoupled. It's a little bit harder to tell from this diagram what the exact accumulated phase is, and so we've provided an additional tool which can show you the accumulated phase between the ions as a function of time. Here we've got to confirm that at the end, the relative entanglement between the ions is pi on 4 as expected. The last tool we provide is one to check the robustness of pulses. To quantify the robustness of a pulse, we provide a quasi-static scan of the infidelity as a function of the error process. Here you can see that both the standard and robust pulse, when there is no error at this 0 point, has no infidelity. This means that the operation is perfect. But as we add some laser detuning shift error, we can see that our standard pulse, which has not been made to be robust, rapidly diverges from having a perfect infidelity. The robust pulse, on the other hand, you can see, has an infidelity that remains very close to 0 for a large number of laser detuning shifts. Using this robust pulse, you can implement it on your real machine and be immune to typical errors like laser shift detunings. All of the results presented in this package have been experimentally verified. Here we can see a result from the University of Sydney lab of Michael Biersick. An experiment was done using a standard pulse and a robust pulse. The standard pulse, once again, as you can see, when there is 0 laser detuning, does the correct operation. Here we're not looking at the infidelity, but rather a proxy, and that is the probability of whether the ion is in the correct state at the end of the Mormon-Sorensen gate. As the detuning error increases, we see that the standard pulse rapidly diverges from having the correct final state for the ion. Our robust pulse, on the other hand, is still robust for a large amount of detuning error. And we can see that there is quite a large plateau where the probability of it being in the correct state at the end is good. The package also allows you to generate gates for a variety of different cold ion system configurations. We provide an example with 5 ions in a trap where we do a parallel gate between a pair and a triplet of ions. We look at 8 ions in a trap and provide entanglement between a set of 4. And then finally, we do an all-to-all gate with 6 ions in a trap where all of them become entangled. This flexibility allows you to consider a whole bunch of different tweaks and optimizations that will really improve the performance of your algorithm on your particular hardware system. And in all cases, we provide both the correct optimized pulses, tools to verify that they are implemented correctly, like phase space diagrams or the mechanical modes. And finally, we can show you the phase dynamics as a function of that.